Hello and welcome back. We're going to continue reviewing Unit 13, Statistics. In the first video we focus on the descriptive nature of statistics. And in this video I want to focus on the inferential aspect of statistics, making conclusions, making inferences about the data from a population. To help make inferences about a population, we do what's called simulations. Okay. A simulation is just a certain number of trials that you take of the same sample size and you get different results. Because when you sample from a population, sampling variability means you're going to have different results. Okay. The end goal is to help us to figure out ways of inferring things about the population, and it turns out that these simulations are really nice because they allow us to see how likely a result is to occur. So, in the real world, we actually do not know anything about the population. We can only take samples to infer values about the population, especially very large populations. If we have a very small population, we're lucky. We can calculate the value, be done with it. Okay? But large populations, we want to sometimes find out things about them. And simulations are used to see the effect from a population that's known, so you can kind of analyze those results to apply them to one that you don't really know everything about. And the results from these simulations appear to always be normally distributed. Okay. Doesn't matter what this sample looked like in the beginning, or the population looks like in the beginning, but the results from the sample are going to be always normally distributed. And anything that occurs in the extremes of the simulations are considered very unlikely to occur. So if I were to look at a set of normally distributed sample means from the simulations, okay, now of course your histogram might look something like this. It might not actually look perfectly normally distributed, but it will follow the general shape of a normal distribution. Then anything that occurs in the extreme high end of the normal curve and the extreme low end of the normal curve is very unlikely. You want our data to fall within 68% of the mean. Okay, 68% of the middle of the data. That's where most of them occur. And that's plus or minus 1 deviation. So anything that occurs in the 16% on either end is considered unlikely to occur. Now if you're over here versus over here, the further you are from the mean or the center of the data, then the more unlikely it is to occur. Now if you were to look at every single sample that's possible from a population of a certain sample size, then it turns out that the distribution of sample means, if you look at all the possible sample means from every single possible sample you can take, those means of all those sample means will be equal to the mean of the population. Okay, and that's an important fact to realize and to know, because if you take a sample, the distribution of sample means is going to be centered around the mean of the population. Meaning it's very likely, to a certain degree of confidence, that the mean of your sample should represent the population. So if we think the population ends up being, let's say we would think the population mean is going to be 250, but we get a sample mean of 150, that's telling me that I'm getting something that's very unlikely. You're in the very end of all the possible sample means from a population. It's more likely that the population mean is actually less than 250, closer to the sample mean. Okay? But it's not impossible to get a sample of 150, it's just very unlikely. And the deviation of the sample means is much smaller than the deviation of the population. In fact, you divide it by the square of the sample size, and that gives you the deviation of the sample means, all possible sample means. So we're going to look at some examples, and I want you, for each of these examples, pause the video and just to read the problem before we solve it together. So pause the video now and read this problem. Okay? So we want to know, is there enough evidence that from the sample that we collected that the mean commuting time is 30 minutes? So we want to know, is mu equal to 30 minutes based upon our mean from our sample? So we took a sample of size 64. We calculated a mean from that sample to be 28. It's pretty close to 30, but we want to know, is it likely to actually get a sample that has a mean of 28 from a population of mean of 30? And my deviation of the sample was 10. I want to see where the mean of 28 compares to the rest of the means. Now the mean of all possible sample means is going to be 30. So there's a couple ways we can approach this. The easiest way to do this is to find out, in relation to the 30, which is what we're predicting or hoping that the population mean would be, in relation to that 30, obviously 28 is lower than there, but how likely is it to occur? Meaning, how likely is it to get 28 or below, because we want to be far away from the mean. So we're going to use our calculators to do this by using the normal CDF, which is under second distribute on the TI-83 calculators. So normal CDF, the min value, I'm going to put negative 1e99, which essentially represents a very, very small number. Our max value is 28. Our mean is 30, and our deviation, we actually didn't calculate that yet, so let me go ahead and do that. Our deviation of the sample means, we have to calculate that value, is going to be the deviation of the population, but in this case we don't know that, so we're going to use the sample deviation because it's very close to the population, divided by the square root of the sample size, which is 64. 10 divided by square root of 64 is 10 divided by 8, which is 1.25. So the deviation we're going to use is 1.25. And then typing this into my calculator, I get 0.0547992894. Okay, and it keeps going, of course. So what this means is that there's roughly 5.5% of all the sampling means, all the samples will produce a mean of 28 or lower. Now that's very unlikely. So what we can say is the answer is no. Okay. If the mean of the population is 30, then only about 5.5% of the samples of size 64 will result in x bar less than or equal to 28. And this is very unlikely. And we can say, therefore, there is some degree of confidence that mu is actually less than, well, it's probably less than 30, yes, because we got a sample mean of 28, and usually the sample means are very close to predicting something about the population. Okay. Now, is it possible the mean of the population is 30? Yes, because what this is saying is there's a 5.5% chance you could get a sample mean of 28 or less, which means it's possible to get a sample mean of 25. Okay, it depends on who you sampled. It's all part of sampling variability. Let's move on to a proportions problem. So again, pause the video now, read this problem, and then we'll work on it together. Okay, candidate A and candidate B are very close to each other, and we want to find a confidence interval in this case, an interval for each candidate that has a 90% confidence to contain the actual percent of support. Now before we do this, let's find out how many deviations away is needed in order to contain the middle 90% of the data. The middle 90% of the data, you want to find out essentially the z-scores that are associated with that percent of the data. Now it's not 1, it's not 2, because 1 is usually 68% around the mean, 2 is usually 95% around the mean, so it might be closer to 2 than it is to 1. We're going to use our calculator to do this by using the inverse normal function. And to do that, we're going to find the percentage. So we want to know the percent in each of the tails. So if 90% is around the mean, that means 10% is left over, which means 5% is in each tail. So the percentile is 0.05. So if I do second distribution in your calculator, the TI-83s, to go to inverse norm, that's going to find out the z-score associated with 5% in this case. And we'll see that is roughly negative 1.64. Now notice, because it's symmetrical, we're going to be dealing with positive 164 as well. Okay, but it's essentially to get an interval that contains 90% of the data, we're going to be 1.64 deviations away from the mean in both directions. Now what this means is for candidate A and for candidate B, we have to find out the deviation of the sample proportions. And we have a formula to do that. Right? The deviation of the sample proportions is found by taking the square root, we're just doing candidate A here, the square root of the proportion, which in this case for candidate A is 45%, so 0.45, times 1 minus the proportion, which is 0.55, divided by the square root of the sample size, which is 500. And if you type that in your calculator and calculate that out, you get roughly about 0.22342784 and so forth. Okay. Now we want to be 1.64 deviations away to contain 90% confidence interval for containing the actual percentage support. Okay, so if I multiply that number by 1.64, I get 0.03664, etc., etc. Okay. Which means from our proportion of 45%, I'm going to subtract off 3.7%. Oh wait, I think I'm doing the wrong numbers here. Yes. Hopefully you caught the fact that I typed the numbers correctly in my calculator, but I wrote the wrong values. We're actually looking for candidate B. It ends up being 0.02222485 and so forth. Multiply that by 1.64, it's 0.036487 and so forth. Okay. So to find the confidence interval of containing the actual percent of support with 90% confidence, we're going to take our proportion of 45 and we're going to subtract off 0.036 and we're going to add 0.036 because that is 1.64 deviations above and 1.64 deviations below. And when I calculate that out, I get 0.414, 0.486. So that means candidate A, let's write it as percents. Percents are nice to deal with. So 41.4% is less than or equal to the proportion of the population for candidate A. It's less than or equal to 48.6%. Okay. Now let's work with candidate B. For candidate B, let's find the deviation of the proportions there. So standard deviation of the sample proportions is going to be the square root of the sample proportion, the population proportion we're testing, which is 0.48 times the 0.52, which is 1 minus 0.58, divided by a sample of 500. Calculating that out, we get what I had before, 0.0223428 and so forth. And again, I want to find out 1.64 deviations away from the sample proportion. And if I multiply that by 1.64, I get what I got before, 0.3664, and so forth. Which means I'm going to take the 0.48, subtract off 0.037, and 0.48 and add 0.037. That gives me 0.443 and 0.517. Right as percents, 44.3% is less than or equal to the proportion for candidate B is less than or equal to 51.7%. Okay. So the question is, based on your confidence interval, which we found, do the candidates have the possibility of having the same percent of support? Yes. Okay. And if yes, how likely is it they actually have the same percent of support? Well, it looks like they have an overlap of 44.3 to 48.6. 44.3% to 48.6%. Now you may notice that the maximum of the interval for candidate A is above candidate A's actual proportion, and the minimum for candidate B is actually below the sampled proportion for candidate A. So I would say yes, it is fairly likely. I would say there is more than 50% chance of overlap in their intervals. Okay. Now, if you had very barely any overlap, then I would say it's very unlikely that they had the same percentage support. But it's fairly likely that they actually do have the same percentage support. Let's look at another aspect of inferential statistics, which is differences in sample means. So again, get a sense for this problem before we work on it by pausing the video and reading it over first. Okay, now in your calculator, you're going to calculate the mean of a frequency distribution by typing in the values in list 1 and the frequencies into list 2. And when you do one-var stats, you have to indicate to the calculator L1, L2. Now, if you have a TI-80 89 or 84, then I believe it asks you a frequency list, and that's going to be list 2 in this case, or whichever list you put it in. If you have an 83 or an 83 plus, you have to tell the calculator L1, L2 after finding one-var stats. Then hit enter, and it'll give you the mean and deviation, all the values we typically get with one-var stats. Turns out that the mean of the control group ended up being 3.22 and 6 repeating. Doing the same thing for the experimental group, we get a mean. This is the second mean, so I'm going to call mean 1 for the first one, mean 2 for the second. That's a mean of 3.026. Now notice we put 75 of the people into a control group and 75 of the people into an experimental group. We got different results, but we want to know, are the results from whatever experimental study we're doing, are they because of natural variability or induced variability? Is the difference in sample means because they are naturally just occurring from natural variability, or are they occurring because we induced some variability? Okay. So, for part 1, for number 1, it says calculate the observed difference in sample means between the two groups. We're going to do that by taking the second mean minus the first mean, which gives us 3.026 repeating minus 3.226 repeating. It looks a little horrible. Let me rewrite that. Minus 3.226 repeating. And what that gives you is negative 0.20. So our experimental group had a mean that was 0.20 less than the control group. Now, the results of 100 simulations were done, and simulations are just taking those 150 people and randomly selecting them and putting them into the control, 75 into the control, 75 into the experiment, calculating the means, calculating the difference. Okay. Doing it again, bunching them up and putting them in 75 into the control, 75 into experimental. Again, random selection, so we're not figuring out ways of dividing them up. It's just a random division into the control and experimental groups. And the results provided a mean of sample differences as negative 0.23 and a deviation of the differences as 1.2. So from this simulation, can you conclude that the difference of sample means is the result of natural or induced variability? Now to do that, we got to find out how likely it is, based upon the simulations, which produced a mean of negative 0.23, how likely it is that negative 0.20 is going to occur. Now negative 0.20 is above negative 0.23. Careful about the negatives, right? So we want to know how likely is it to occur. So we want to know how likely is negative 0.20 or above likely to occur. So I'm going to use my calculator. I'm going to use the normal CDF. My lower bound is negative 0.20. My upper bound is infinity, positive infinity, so I'm going to use 1e99. You could use a really large number if you want to. In this case, a large number might be considered 6, or even 10, or 1,000. Okay. The mean is negative 0.20, and the deviation is 1.2. Now typing that in my calculator, I get 0.4900274339. Now that's really close to the actual mean. So I would say the results from the control and experimental group were due to natural variability. The way we would know if it was due to induced variability is if you get something that's in the extremes of the natural from the simulations, because the simulations are indicating the natural variability. So using results from above, what can you conclude about the experiment? Okay. Well, you can conclude that the control group had about the same results as the experimental group. You can go the other way too. The experimental group had to say about the same results as the control group. Okay. So really, what that means is that the conclusion of the study that whatever we're looking at and we're trying to experiment is really just occurring because of natural variability and not induced variability. Pause the video and write down anything you need to before moving on. Now, margin of error is going to be used to find an interval that contains, with a 95% confidence, the parameter of interest of a population. The margin of error, because 95% contains within 2 deviations, is always going to be found by taking 2 times the standard deviation. Okay, it's either the deviation of the sample means, or margin of error is going to be the 2 times the standard deviation of the sample proportions, our p-hats. So I have one example of each. One is sample mean, one sample proportion. So sample size 50 provided a mean of 356 and a deviation of 61. Find the margin of error of the sample and then find the 95% confidence interval of containing the mean of the population, mu. So I got to find the standard error of a standard deviation of the sample means. And that's going to be found by taking the deviation of the sample, which is 61, divided by the square root of the sample size, which is 50. And that gives me roughly about 8.6267, etc., etc. So the margin of error is going to be 2 times that value. And that gives me roughly 17.2534. So the question becomes, what's the 95% confidence interval containing the actual population mean? Well, we have to add and subtract that margin of error from the sample mean of 356. So 356 minus, let's deal with the hundredths place. Okay, 338, 17 points. Get my head of myself a little bit. Minus 17.25 is equal to 338.75, and then add 17.25. That gives me 373.25. So the margin of error, let's say, ends up being 17.25, and then the 95% confidence interval containing mu is going to be 338.75 is less than or equal to mu is less than or equal to 373.25. Right. Now let's look at an example with sample proportions. We have to find the deviation of the proportions. That's to be found using the formula. The deviation, the proportion of our sample gives us 0.25, and then 0.75 is 1 minus 0.25. It's a little better. It's kind of hard to write with this pen really small. I'm zooming in to write more neatly. Divided by a sample size of 80, okay, and that gives us 0.0484122 and so forth. Okay. So our margin of error is going to be 2 times the deviations of the sample proportions, which therefore is roughly about 0.968. Oh, sorry, 0.09682 and so forth. Okay. So I want to know 95% confidence that contains mu, the population proportion, P in this case. So I'm going to take that sample proportion, 0.25. I'm going to subtract off to nearest hundredth as well. 0.10, add 0.10, which gives me 0.15 and 0.35. So our margin of error ends up being 0.10, and then our confidence interval of containing P is going to be 0.15 is less than or equal to P is less than or equal to 0.35. You're 95% confident that the population proportion is actually between those two values. Now let's move on to determining regression equations. Now, I want to just draw a picture of each of the basic types of regressions to use before looking at some regression examples. A positive linear regression is going to be found when you see a scatter plot that looks kind of like this. Okay. Essentially, you have a line that best fits the data. A negative linear correlation occurs when you have points that look like they lie in a line, but they are going down. They have a negative correlation. Okay. So to draw in the line of best fit, it would have a negative slope. Okay. Another common type of regression is the quadratic regression. That occurs when something looks like it's going to be arranged in a parabolic shape. Rises and then falls, or falls and rises, because if it's a positive or negative parabola, you can have either. But the general shape, the general trend of the points follows that of a quadratic functions, which is all the parabola as well. And exponentially, you really have two. You have exponential growth and decay. One of the common types of exponentials in science is a decay equation. Half-life. So you might see a scatter plot look like this. And the general shape of that is that it starts off high and then starts leveling off, but it's decreasing. It's not linear because you can't just draw a line through it and fit the data as best you can, but the points kind of follow an exponential equation. Now you could essentially have an exponential growth by having something that looks like this. Okay, depending on the data and how it looks, it may look like an exponential growth or decay. Now logarithmic is the inverse of an exponential, so it's something that kind of looks like this, where it's kind of curving up to a value, but it will actually never reach that value. Okay, so it looks something like this. Okay. The last one is the sinusoidal graph, and it doesn't really matter where it starts, but essentially if you see points that rise and that fall, and then it seems to rise and fall again, it's starting to follow a sine curve. So the whole point of these scatter plots is to kind of, is to determine, which type of regression do you actually have. And you can use your calculator to type the data into L1 and L2. Go into your calculator, turn stat plot on to plot it. Make sure you find a good window. And then using that stat plot, you can find out generally what is the trend. Is it a linear trend? Is it quadratic, exponential? That determines which regression equation to use. Now, regression equations, sometimes you're going to be asked to find a certain regression equation, like say, find the exponential regression equation, or find the sinusoidal regression equation. Or it might just say, determine the regression equation that best models the data given. So go ahead, type these into your calculator, find the scatter plot, and think about which line best fits, or which regression equation will be the best fit. Now you may notice the scatter plot looks something like this. To me that looks linear, so I'm going to do a linear regression. And doing that, we're going to round our values to the nearest, let's say, hundredths place. Okay. To the nearest hundredths place, I get a regression equation of negative 2.55x plus 55.96. There's my regression equation. Now, to determine if this actually is the best equation or if another one is a better fit, you could always make sure your diagnostics is turned on. So you have to go to a second catalog, which is by the 0 button on the TI-3 calculators. Second catalog, and then turn your diagnostics on by scrolling down to diagnostics on, hit enter until you say done. Then we do the linear regression. You'll see that the R value here is actually negative 0.996 to the nearest thousandth. And that's a very strong negative linear correlation. If you were to do a quadratic regression or exponential or log, what you're going to look for is the R squared value, not the R value. Okay. In that case, you get something that's less than 0.996. Okay, so linear is the best fit. I believe quadratic regression is 0.99296, which is really close. But if you look at the equation, you'll see that the coefficient of the x squared term is really small. Okay. And the rest of it looks very similar to our linear equation. Not exact, but very similar. which essentially means that you can model with a quadratic, but this, because it's a really small coefficient, is really essentially 0. It's not there. Okay, so don't be fooled by that. Now the next part says to find the data that's associated with an input of 8. So all we have to do is plug in 8 for x, y equals negative 2.55 times 8 plus 55.96, and that gives you an output of 35.64. Now notice I'm plugging in 8, which is within the range of my data in my table. It's within the domain, the range of values in the domain in the table. This is something that's called interpolation. That occurs when you're finding results of a value within the given range of the given data that you use to find your equation. Okay. Now for number 2, pause the video, see if you can plot the points and figure out which kind of regression this is going to be. Okay, hopefully by plotting them into your calculator, you can see that the graph looks something like this. It looks kind of all over the place, but it looks like it's kind of rising and falling. If you really look closely to it, it looks like it's rising and falling like this. Okay, it looks sinusoidal in nature. And in fact, it is a sign regression. Okay, so to do sign regression. In this case, even though we don't have equal intervals, we don't know what the period is, so we're kind of forced to just do sign regression without where the period is. Okay, but again, if this is a problem dealing with an interval over a whole year and you're dealing with days, put in a period of 365. Or if you're talking about over a course of a day and you're dealing with hours, put in a period of 24, because that's what we want to have happen in our equation. Okay, but this we don't know, so we just do sign regression and get an equation. And the equation, rounding all values, let's say to 3 places, gives me 24.613 sine 0.313 x plus 1.137. And parentheses plus 49.659. Okay, now if I did that correctly, copied it down correctly, and that's what we get for the regression equation. Again, it says here predict the value associated with an input of 8. Now I'm plugging in 8, you have to remember that the regression equation that's given to you is in radian mode. So you have to make sure your calculator is in radian mode to find the predicted value associated with 8. Plugging in 8 for x, we get y is equal to 73.3889. Okay. Now notice 8 is not within this data value, the given data. It's actually lower than the minimum, which is 14 for an input. So this is called extrapolation. It's important to know those terms, and that's going to be less reliable than interpolation, because interpolation is dealing with something that's close to what was given to you, so your results should be pretty close to what we expect. But anytime you deal with extrapolation, then you're dealing with values outside the given data, which means you're going to have some errors occurring. Okay, so let's sum up the most important information from this unit. Okay, so pause the video now, make a sense for this before we conclude the review videos. Okay. As you see, there's a lot going on in the stats unit, and it does make up roughly about, I would say, 15 to 20% of the Regents exam, so just be prepared to work your way through these problems. And I want to thank you for watching these review videos. I hope that you have found them helpful for you, and I wish you the best of luck on the Regents exam coming up in a few weeks. Thank you very much.